All right, I guess we're good to go. Everyone ready? All right. Hi, I'm Ryan Stortz, and this is Swift Reversing. This talk is about the Swift programming language, not the interbanking network. If I were doing that, none of you would know, and I'd have a solid good laptop. So this talk is broken into 3 parts: an introduction to Swift, a discussion of my methodology in reversing the language and the ABI, and the actual results from my research. So Swift is Apple's new sexy language for the future. Just like everything Apple does, it was more ceremony than substance when the first version was released. Raise your hand if you had an iPad 1, an iPhone 1, or an Apple Watch. You know what I mean. But more importantly, Swift is meant to take over for Objective-C, and if you've done Objective-C reversing or development, you can probably get behind that. So Swift was actually open source back in December before I started doing a lot of this research. I did cheat a little bit afterward. I don't know if it's really cheating. And go verify the things I had discovered originally when it was still proprietary. It's technically available on Linux as well as OS X, but so is Objective-C, and that didn't go so well. So we'll see. And a few months ago, MacRumors actually had this big article saying that Google is considering adopting Swift for Android. I think that article was in February, and I haven't seen anything from it again. So I don't know. Maybe that's just like a random MacRumors TechCrunch kind of let's pump the stock kind of article. Swift is pretty expressive. You can commit atrocities like this one. This is Noah's Ark. You can see that there's the world. There's all the animals in the world. We have a boat, which is an array of strings. For love in world, we're going to put 2 of each on the boat and print the boat. The output is below, 2 by 2. So Swift is meant to be a systems programming language. So things like these awesome emojis actually get compiled to machine code and are executed natively on the platform. They're not interpreted and they're not, JITted like in Python or Java, respectively. So Swift, the language, it's a modern language, which I'm not really certain what that means, but I think it was designed after Smashing the Stack for Fun and Profit came out and told everyone that memory safety is a thing. I mean, sure, there was stuff before that, but it has all the features you'd expect, like closures, first-class functions, tuples, generics, easy iteration, error handling built in. As a reverse engineer, I was reading the feature list, and the closures and generics came to me those made me concerned. I felt they'd be problematic when reversing, because if you ever reversed highly templated C++, you'll know what I mean. And these are, Swift's version of those. Swift also makes heavy use of optionals. Optionals is a form of error handling where it is a boxed object that either has the value you want or has none, and you have to safely unpack it before they give you the data. I felt that this was going to add a lot of noise to the assembly, so I spent a lot of time figuring out exactly how optionals are represented, and I'll get into that. But first, I wanted to go over the compiler stuff. So I actually got into Swift because I was doing a lot of LLVM development, a lot of low-level analysis passes to try and find code patterns that might be, vulnerable, and to rewrite code to be obfuscated, things like that. And I felt that looking at the compiler setup was important to fully grasp Swift reverse engineering. So these next few slides kind of go over the compiler architecture and borrow heavily from Chris Latner's LLVM dev meeting presentation. So both Clang and Swift and Rust and a million other compilers are built on top of LLVM. Clang has a pretty minor set of minor, overhead on top of LLVM, where Swift has a much longer chain in front of it. The optimizations for each, happen in very different spots. Swift, was designed by the same people who did Clang and LLVM, and they learned from their mistakes. And one of these mistakes is they implemented their own intermediate language they had a full understanding of Swift's type system and could do some guaranteed optimizations and some safety. So where Clang optimizes here, Swift, with all of this extra information, is able to optimize here. And each one of these optimizations actually causes a lot of problems. Every time they have a closure or just even a regular basic block, it can be optimized in 80 different ways. And when you reverse engineer things, you kind of pattern match things. You don't really go in and like, okay, yes, this one is iterating from 1 to 4, it's indexing to this array. Like, you kind of pattern match to like realize that like, okay, this is just iterating over this array, and that is then passed to this function on each iteration. So going through the compiler, we start with a Swift source file. This gets parsed and lexed and becomes an AST file, or abstracted syntax tree. This is not meant to be machine read or human readable. It's meant to be machine readable, but it's a nice tree format. You can still see the emojis. That goes through the SIL gen. So the first layer is AST to SIL, which is Swift's IL. So Swift does all of its analysis on SIL. And if you're familiar with any, IR or LLVM, you'll notice that this one is a bit higher on the abstraction layer. Like, it understands types. It understands the stack. It has like things like the enum optional, and it has virtual function pointers haven't been like devirtualized yet. Things like that make analysis much easier. That ends up going to LLVM IR. This is just normal LLVM IR. And then finally to machine code. So this is x86-64, AT&T syntax. I'm sorry, I didn't change that. And like, that's the whole thing. And there's chances to optimize and rewrite the code in many stages. One last thing about SIL before I go to the actual talk again. Alloc box. So Swift has many ways to create closures. SIL has the alloc box optimization, which actually causes a lot of heartache when reversing. So by default, all variables are allocated on the heap, much like Java. And everyone knows how fast and expressive Java is, right? Well, Swift didn't want to do that, so they do guaranteed analysis for escape analysis. And if a variable doesn't leave a scope, like let's say the function scope, they're going to take it off the heap and bring it onto the stack. And this means there's 2 or 3 different representations for each variable or closure type, and this multiplies across your entire application. So enough about the compiler. Let's figure out how to turn the thing on the left to the thing into the right. And these are actually the same thing, starting with my methodology. So I promised a systematic approach in my talk abstract, but it was more a list of things that I was confused about going in. To start, you really need to start with motivation, because you could be like language weenie and want to know every little detail about how the language is constructed and dissect the decisions made by Latner and Groff and whatnot. But what's the motivation for that? The research really needs to be driven by the work that you want to do. So when I start reversing things, I start with one of these first 2 in mind, application pen testing and exploit development, but I frequently end up just finding myself building character, which is my, I don't know, pep talk way of saying not making progress. So this talk focuses on application pen testing, but there's a lot of character building. Starting with my initial questions. So I jotted down a bunch of questions going in with the language. So what areas, and I broke them down in 3 areas. So the toolchain, the language core, and the ABI. So what tools are available? What is it message-based, like Objective-C? What native types are available? How does Swift bridge into Objective-C? Because I know that they are compatible with each other. What is the calling convention? How are things laid out in memory? All these are initial questions I had going in. For each one of these questions, I created one or more small project that focused on using that one individual feature behind each question. For example, this one is optional unpacking and class inheritance. So you'll see that there's a vehicle-based class, and bicycle inherits or is derived off of that, and tandem is derived off of bicycle, and each one extends the next. This one has a small closure. It actually has 2 small closures and several bugs that will cause it all to crash if given the right information. But this was another example I used. So going into the actual reversing, I started by looking at any tools that may be available already. Tools that might help reversing, but also just creating things and being environments to debug in. And it starts with Google search and Swift reversing. 9 of the top 10 results were reversing a string array in Swift, and the 10th one was about Taylor Swift, reversing female opinion and why women love her now when they didn't 3 years ago. So I was kind of, on my own there. So to start, I looked at the compiler, and the Swift-C is a compiler. It's installed with Xcode. There's a Swift application, which is the compiler REPL, which is fun to play in. And then there's swift-demangle. Nothing really else was available at the time. They do have some nice diagnostics that you can dump, and you can dump the SIL, and you can read the SIL and try to make sense of that. And at the time, it wasn't documented at all, so it was not all that useful. What was kind of useful is things like the Swift REPL, and I guess there's I'm too far up the screen on both of them. The Swift REPL was neat because you could type in things, and then if you prepended things with a colon, you could dump into LLDB. So you could then disassemble at PC after you had assigned some variables, and it also caught errors. So what I do here is actually I assign v as an optional int, and I give it 2, and I assign x as an optional int, and I give it nil. Force unpack v, I get 2. Force unpack x, and I get an exception, which is what you expect when you force unpack something that's not there. The most useful tool actually was swift-demangle. So if you've done C++ reversing, you know that in order to have functions with the same name but different parameters, they have to mangle the name and then code the type signature in the name, and you can demangle that via standard tools like C++ filt. Well, Swift has the same thing, except it's actually much more expressive. You may notice at the bottom here on the second one, arg1 equals dead. It actually encodes the ownership of the argument into the type signature, and also all of the types of all the arguments, and they're very expressive. They're not just void star or int star. This is a first-class function passed in that takes these arguments, and it's a specialization of this class that then it assumes that arg1 is no longer maintained after you pass it in. So if it wants it to not get deallocated, it's responsible for that. And it's got this neat tree view, and it's meant to just be garbage on the screen. Don't try to read it. But if you're into parsing things and writing tools, this is fantastic, because nothing like that exists for C or C++. So initial tools, questions, revisiting, what tools are available now is nothing. It's just swift-demangle. There's class dump, and class dump kind of works because of the binary compatibility between Objective-C and Swift, but it gets very confused, and it shouldn't be too difficult to update, but I haven't done that yet. Yeah. Next up is the language core. Look at this little guy here. It's what comes up when you search a language and set the image settings to the right size. So language core. There's a billion things I could put here. I decided to focus on native types, control flow, and optionals in class instantiation. A lot of these native types decay into Swift built-in types, which then decay into LLVM native types. So they're kind of what you'd expect. Like an int 8 is assigned 8-bit integer on a little endian system. And you know, they actually, like all of Swift is UTF-16, but they decay into UTF-8 because that is more easy to optimize, and the CPU can deal with that natively with like ASCII add after dish and all that stuff. So they'll decay into that if that's all you're using is UTF-8. And like I said before, for each language feature, I want to know more about a test case or two. So Objective-C actually does use, I skipped this. Objective-C uses tagged pointers that encode like reference counts and maybe types in them. Swift doesn't use that, even though it'd be cool. And it's a built-in feature in ARM64. So the first question I had was messages and laziness. So when you do Objective-C, like this one down here on the bottom one, you get these weird indirect calls that are very difficult to follow. You get an object that's passed Objective-C message send and then a string reference. And that, in the back end, dispatches a call to that function. Going the other way is not always the easiest. And then getting type information is not always the easiest. And figuring out how many arguments is not always the easiest. And it's super annoying. And Apple, you know, rightly decided to get rid of that. And so messages aren't a thing unless you're bridging to Objective-C. And then for laziness, there is no laziness, which is awesome. If there were laziness, you'd end up with a bunch of Haskell-style thunk chains. I have tried to reverse engineer Haskell. I wrote a Hello World program, and it took me an hour to find the string Hello World via tracing calls and references. It is a level of hell that Dante didn't quite describe. So I don't wish that on anyone. Optionals. So optionals are awesome. C++ 17 and 14 have these, and everyone should use them and get rid of exceptions and get rid of return codes. Just use optionals everywhere. Because they enforce, for lack of a better word, a good design paradigm. And, you know, everything requires them in the Swift native library. You can unpack them. Like, this is a safe way to unpack them right here, is if let name equals optional name, and then you get access to name, it's bound in this one scope. If it's not bound, it actually skips this block. And then we have a little bit of pattern matching here. So we have choice is passed in as possibly an integer from arguments, and we match it to 1, 2, 3, or invalid choice. So these are actually encoded in a much simpler way than I expected. I expected them to be loud and ugly and horrible in every way. They are quite thin. They're just 1 byte. And you have your value encoded, and this can be several, I'll do this one. This can be several bytes. I think it's up to 24 bytes decimal in line, and then you'll have your optional flag. And if the option is there, like if the value is available to you, the flag is cleared. And if it's not, it's set. And the code is littered with these like and one, these bitwise ands of random things. This 51 right here is correlated with this 52. So if the option is clear, if clear, retain it. And the great thing about that is the only place that uses bitwise ands in all of Swift code is optional unpacking. Something that scared me going in ended up being much, much easier to reverse. What does suck is you end up with these like weird misaligned structures. So like this is an int 64 with a value 2, and the option is in the next byte, and it ends up getting alignment. There's a lot of dead bytes everywhere. Yeah. The other cool thing is the compiler emits a UD2 or bug in hexarrays anytime you use an option in an invalid way. So this one is take an integer off of process arguments, cast it to an optional integer, force unpack that. We see here that we force unpack it, and if it's set, meaning the option was not parsed properly, it hits this bug. And you'll see you get a legal instruction if you do it. And this totally says Shaka Khan, not infiltrate. Next thing I wanted to look at is dynamic class allocation instantiation. So as you'd expect from a high-level language, you don't really handle raw memory operations yourself. And it turns out the way that Swift handles this isn't very much different than C++. You'll hear me say not different than C++ a lot because I was very surprised going in, having suffered through Objective-C. The minor differences actually are related to accessing the type and passing that to a Swift alloc object. In most or maybe all cases, you'll see that they use an allocating init form of the call, which will handle everything, which it will handle allocating the object, assigning its vtable, and instantiating all its members, and then going up its inheritance chain and doing the same for all of that. Interesting though, in V1 here, the alloc call cares about the type. This is great because you can now just cross-reference every call to alloc object, and you get like, oh, classes.train is 24 bytes long. And it also has this is a alignment mask. It is aligned to 8-byte boundaries. And if you've done this before, you're like, you have to cross-reference a bunch of stuff. You have to do like horrible subtree matching in X-rays, or that's what I've done. It's probably not the right choice. Going through this, I found this awesome comment, which is, at some point soon after return, it will become an invariant that metadata get size will equal the required size. And it's like, what do you mean sometime after return? Like, is this getting allocated by another thread? Is this a possible bug area? Right now it's not, but in the future it might be. Because right now it's just backed by a slow malloc. But they might allocate something in the like on demand or in another thread in the future to speed it up even more. But I'm totally waiting for them to optimize it and remove their to-dos, because that's what makes us money. So this is a class instantiation, and specifically it's the non-allocating version of trains in it. It calls its parents non-allocating in it as well, and it assigns the parent's pointer. And this is hexarrays getting confused. This actually doesn't have return address or return type. And in C++, this function would be responsible for assigning the class's vtables, but in our case, that's handled by Swift alloc object. We also get a lot of these lazy bound variables, where if this guy has not been set, they set it, and then just return it. And if it has been reset, set it, they look it up and return it. A lot of those get optimized out at higher optimization levels, but they're super verbose and awesome. I love all the symbols. So language core revisited isn't message-based like Objective-C or more like C++ and C++. Is it lazy like Haskell? No, thank God. What native types are available? The usuals that you'd expect. The rest, bitwise ands for optionals, all that. And the final area that I looked at was a Swift ABI. This is where, so the ABI is the application binary interface. It defines how compiled applications talk to other compiled applications, like how you, what registers, and you put your arguments in, like arg1 goes into RDI, or R0 or something like that. Return values come back in RIX. So since I'm dealing with machine code, the ABI is important. So my questions with the ABI is, how is Objective-C bridging done? Almost all of Apple's code is in Objective-C still. And I think that's because of backwards compatibility reasons with like ARC stuff. How are virtual function calls implemented? Big pain point. Who owns what in arguments, and what's the calling convention? Bridging. So bridging was actually really difficult to do on the command line. I did eventually get an example working, but I had to cheat with Xcode. So Swift is very far away from being like a command line server application kind of thing like you'd kind of want with Linux if you're doing it with Linux. Here I create an Objective-C class that implements one method, and I call that from Swift. So bridge test is one method. It has a class method called class method 1, and this is the compiled bit of that function. Notice the funny bit of mixing and matching. We have a Swift style allocating init, and then right after that we hit Objective-C message send and Objective-C release, and then like Swift doesn't know what to do. If it ends up returning a untagged pointer, it calls Swift unknown release, and if it's tagged, it just releases it. I have that backwards. If it's tagged, they unknown release it, and if it's untagged, they release it. Did I just say the same thing twice? Here's the Objective-C class for reference. It's trivial. It just calls this native like syslog, nslog function. Virtual function calls, everyone's favorite. They're implemented identically to C++. Your instantiated class has a pointer in a table. That table, has a bunch of function pointers. The index of it, corresponds to the call you want, and you index into it and call a method. And this hexarrays code right here corresponds directly with this guy. So we see 2. They've already unpacked the optional above this. 2 equals choice. We'll instantiate a train object, and we'll call train.makeNoise, and that's done through this virtual method. Ownership rules. Object ownership rules are pretty well defined, which is one of the major reasons why it's so safe. Everything in Swift is reference counted with ARC, which is Apple's automated reference counting. A lot of the old Objective-C bugs are the fact that ARC was not required until, I think it's just now becoming required. Well, that's not true. Not everything's reference counted. Native types aren't. And also stack objects that aren't reference counted. That don't escape aren't reference counted. And this is possible because almost everything is derived from this heap object type, which includes a ref count, a data pointer, a type field, and some inline storage if it's a smaller object. And all of the ownership rules for like external calls are encoded in the type signature. So we have dead, guaranteed, exploded, guaranteed, and exploded, which are funny names. Dead means the caller doesn't maintain the reference. Guaranteed means the caller maintains the reference. Exploded means it got unpacked and it's dead. And then guaranteed is, guaranteed and unpacked. There's a calling convention. Swift's approach is awful. They will do whatever the hell they want at any time, and they don't care what you're doing, and it's awful. But it makes sense to make it faster, because if you have valuable data in one of your calling or callee safe registers, you want to keep it there rather than like just change the one calling spot. Hexarrays doesn't understand it at all. So variables appear out of nowhere on a read from, but then on closer introspection, they're actually the return values from the preceding call, and you just end up having to go in through every leaf function and type them all properly. And it's awful. Sorry, flashbacks. Who has been to this page in the IDA Pro documentation? I'm pretty certain it's just me. IDA has support to do awful stuff with variables and their type signatures. And I've done that to get it working with Swift, except it only works with 3 arguments, and by default, Swift needs 4 as registers. So it doesn't really work in hexarrays yet. And I've bugged Igor and Ilfak about it, and they're not doing anything yet. So ABI revisited. It bridges seamlessly. It's C++-like. Classes and structures, I guess I didn't cover this, is laid out exactly like Objective-C. Actually, if you want to do more Objective-C stuff, you should just go read the Swift docs, because they're well formatted and they're easy to jump into, and they actually put a lot of invariants on Objective-C in the future, and those docs aren't available for Objective-C at all. And the calling convention is YOLO. Tools, so there are no tools. I wrote a tool, it's called swift.py. I hate writing IDA Python, but I had to. This is actually IDA hexarrays Python. Yeah, so what it does right now is it does hexarrays rewriting of demangled names. It annotates the IDA disassembly with these demangled names. It does some class body recovery, and it does some type propagation, but that's really broken, so for this demo I don't have it on. And it will do witness table recovery once I fully understand the implications of witness tables. And I have a small demo for that. Let's see, this is gonna work. So what it's doing is it's moving my Python file out of the plugins folder. I have this this Swift program that was where I was playing with protocols. And you can see all the names are mangled, hexarrays, you have no idea what's going on. Like you can kind of see like, okay, there's something in protocols called dice. There's an LCG, it's probably random number generator for dice. And then not a lot else that you can figure out what's going on. Close that, it's moving my plugin back in, relaunching it. And you can see like, okay, we have a little bit more here. Not all of these are working perfectly, but we can see we have a protocol witness table for the dice. We are calling, we're allocating a dice object. We are getting the textual description of it. I believe we throw the dice somewhere as well. So it goes through and rewrites that. We also can run it on here, and you'll get it in the disassembly as well. There's no way to add your own name demangler in IDA. I've also complained about that. So this is what I'm left to, and it'll get classes eventually. I don't think I have them here. Yeah, there's a few that it got. Swift double, Swift LCG, things like that. The demo is super simple and short, so that's it. I tried to make the talk a little more interesting with super dry humor. But, you know, it's a very dry topic. I hope you guys enjoyed it. Swift still has some hurdles that need to be crossed in order to be able to effectively reverse engineer it and re-implement Snapchat. So that's my talk, and this is me. Do you have any questions? No. All right, cool. Thank you.